want to tell you about most ophiolites reflect subduction initiation and formed in the last billion years. So many people already know what an ophiolite is supposed to look like, and some of them do look like this, but very few of them. Most of them are not so beautifully preserved. And what you can see here, I hope you can see my little cursor, is, the crustal section, layer 2A, layer 2B from the oceanic geophysics, the lower gabbros, and then the ultramafics, which are all part of the mantle section. Now that is our textbook ophiolite, which we teach to students. But the reality, so this is a map from Furness et al. 2014, beautiful map showing all of the ophiolites of different ages. These are very important features. They are global features. They are something that all geologists that work on tectonic problems are interested, and they're on every continent. Maybe not in Antarctica. I don't think we found one there yet. Now, there are two ophiolite challenges. One of them is because ophiolites form by seafloor spreading, the importance of ophiolites for tectonics has been recognized since the early days of plate tectonics. Challenge one, how do we confidently identify ophiolites? Most of them are structurally disrupted, and sometimes it's very difficult to convince other people that what we call an ophiolite is an ophiolite. Sometimes because what we call an ophiolite is not an ophiolite. So, and then challenge two is, where do they come from? This is a very interesting snapshot of the history of our science. So in the 1960s and 70s, most ophiolites were thought to form in mid-ocean ridges. And then as people started to get better and better geochemistry, we could see that the composition of ophiolites had certain elements that were quite different than what we expected from mid-ocean ridges. They had certain enrichments that required they form over a convergent margin, the subduction zone. And that dominated our thinking about ophiolites in the 80s and 90s. And then the idea that forearcs formed during subduction initiation is something that is developed, as I'll show you, and we now think that most ophiolites form in forearcs. And it may be that we still underestimate them. So we have a range of ophiolites from extremely beautifully well preserved ones like Oman, the best ophiolite in the world. Look how big this is. Look how intact it is. There's a reason people go there and study it, because it is so spectacular. But then most other ophiolites look more like this. So this one is, you can definitely see deformation, and you maybe struggle to figure out what it was originally, but there's a whole range of ophiolites. A few of them are beautifully preserved. Nearly all ophiolites are disrupted. Some are very unconvincing. So how do we separate the wheat from the chaff? The real ophiolite from the bad ophiolite, the non-ophiolite. So the answer is to compile data for ophiolites and score them. And Kent Condi and I last year wrote a paper about ophiolites, and there are many papers about ophiolites summarizing them, but our contribution was to develop a scoring system that would allow anybody to give a score that could be compared with any other ophiolite. So I think this is free for download, Geoscience Frontiers. So this is the idealized ophiolite of Furness and Dillick, 2022. And this is our scoring system. So it's an 11-point system. So if there's pelagic sediment on top, that's 1 point. If there's pillow basalt, that's 1 point. If there's sheeted dikes, that's 2 points. Some evidence is stronger than others. If there's plagiogranite, that's 1 point. If there's layered gabbro, that's 1 point. If potiform chromite is in there, we give it 2 points. If there's depleted mantle, Hartsbergite, we give it 2 points. And if the publication describes it as an ophiolite, you get 1 point. So the perfect score is 11. You know, Oman is an 11, but most other ophiolites do not score 11 points. So these are the 277 ophiolites that we compiled and the scores we gave them. So the scores range from 11, the maximum, that would include Oman, down to 1. So that would probably be an ophiolite. That the only evidence there was that it was an ophiolite was that somebody called it an ophiolite. The rest of these characteristics, expected characteristics, didn't exist. So we can break these into ophiolites that get a score between 8 and 11. These are confident ophiolites. Ones that get a score between 8 and 6, these are probable ophiolites. And ones that get a score of less than 6, these are questionable or unlikely ophiolites. So of the 277 ophiolites that we found in the literature, 226 of them score 6 or more. So they are, you know, probable and confident ophiolites. Now, when we look at these ophiolites with confidence levels greater than 6 over Earth history, we see that the vast majority of them are younger than 1 billion years. This is something that's been noticed before, but there are ophiolites that extend back into the Neo-Archean and even one back here in the Paleo-Eoarchean. But it's a general result that most ophiolites are less than 1 billion years. So now the second challenge is, where do ophiolites form? Now, Furness and Dillick in 2022 identified these. Actually, this one was a volcanic arc ophiolite, which doesn't exist. This would be replaced by the back arc basin ophiolite. So the mid-ocean ridge type, according to their compilation, is 20% of all ophiolites. 7% are back arc basin ophiolites. 73%, and this percentage keeps increasing, are Forearc type ophiolites, which I'll be talking about for the rest of this talk. And then less than 1% are plume type. And according to their calculation, their compilation, there is no evidence for a continental margin type of ophiolite. So ophiolite form in what becomes the forearc during subduction initiation. So it's easy to emplace an ophiolite if they form in the forearc. But how and when do ophiolites form in forearcs? And we figured it out in the Izu Bona Mariana forearc. I think you can see Busan is down on this part of Korea, and the Izu Bona Mariana arc extends from Tokyo, Japan, down to Guam, USA. And it's the forearc in here that provided the best evidence. So how does that happen? Well, this was the main elements of it were worked out by myself and Sherm Bloomer back 30 some years ago. So we have two oceanic lithospheres separated by each other. This could be a piece of continental crust. It's buoyant relative to this. And there's some kind of a lithospheric weakness that allows the old dense lithosphere, which is negatively buoyant below relative to the underlying asthenosphere, to start sinking like this. So this is the situation for the IBM at around 52 million years ago. And then by about 50 million years ago, it was doing this. So this downward flexing of the old lithosphere creates this space in the overriding, what becomes the overriding plate. It's not a subduction zone yet, because the motion, as you can see, is vertical. And that allows the asthenosphere to flow up and fill in here, melt, and generate melts and seafloor spreading to make ophiolites. That's where ophiolites form. That's when and how they form. So later, as the sinking continues, eventually it becomes favorable for the vertically sinking oceanic lithosphere to start moving down dip, and you see that here. This is true subduction. There is no true subduction until the plate starts going diagonally, not just vertically. Very important point. And at that point, the entire forearc is no longer subject to nearly as much extension, and it cools, and it becomes the normal form. So let's watch a 3-minute video. This is a geodynamic model by, and let's see, get it back down there. And I hope you can hear the sound.
How do new subduction zones form? A subduction zone is where an oceanic plate, or lithosphere, sinks into the mantle. The sinking of oceanic lithosphere powers plate tectonics, and is where the most powerful earthquakes, tsunamis, and volcanic eruptions occur. In this video, we show one way that a new subduction zone can form when dense oceanic lithosphere sinks adjacent to a major lithospheric weakness, such as a transform fault or fracture zone. We show the results of a two-dimensional computer model generated by Professor Taras Geria's group at ETH Zurich in Switzerland. This is how the experiment is set up. Notice that the box is 5,000 kilometers wide, but only the middle 800 kilometers are shown. Similarly, the box is 1,200 kilometers deep, but only the top 220 kilometers is shown. Thin young lithosphere is found to the left of the fracture zone. Because this lithosphere has a thin mantle root, shown here in dark blue, it is buoyant compared to the underlying asthenosphere, shown in purple. Thick old lithosphere lies to the right of the fracture zone. Because it has a thick mantle root, it is slightly denser than the underlying asthenosphere. This lithosphere is gravitationally unstable and should sink, but its strength makes sinking difficult. Let's take a closer look at the formation of this subduction zone. Slowly, the old lithosphere begins to sink next to the lithospheric weakness. Eventually, the asthenosphere begins to flow over the sinking slab, where it partially melts to form new oceanic crust by seafloor spreading. This eventually becomes the forearc. It is also where most ophiolites form. As the slab continues to sink, it encounters increasing resistance from the underlying mantle and begins to move down dip. This is where true subduction begins. Once true subduction begins, seafloor spreading in what becomes the forearc stops and the underlying mantle begins to cool. As subduction continues, the magmatic arc begins to form about 100 kilometers above the subducting slab. This is the situation we see in mature subduction zones, which are very stable systems and can exist for tens or even hundreds of millions of years. We hope you enjoyed this explanation about one way that a new subduction zone can form. If you want to learn more, please read the papers listed at the end of this video. If you like this, please consider subscribing to the UTD Geoscience Studios YouTube channel.
Okay, now I want to show you an application. This is another 3-minute video, and I think you'll find it interesting.
The spectacular Himalayas are the highest mountains in the world, separating the lowlands of India to the south from the Tibetan plateau in the north. This incredible mountain range can be traced for 2,400 kilometers, or 1,500 miles, and includes more than 50 peaks over 7,200 meters, or 23,600 feet above sea level. The Himalayas are all the more impressive because of the rocks that formed them, and they have risen from where they were deposited on the seafloor during the Mesozoic era, the age of the dinosaurs, more than 65 million years ago. What caused this greatest of all Earth's mountain belts to rise out of the sea? We have known since plate tectonic theory was established 50 years ago that the Himalayas mark where two continents, India and Eurasia, collided. It was this collision that uplifted the Himalayas to their incredible heights. We also know that before this continental collision, India was part of the supercontinent Gondwanaland, separated from Asia by thousands of kilometers of a great east-west ocean called Tethys, named after a Greek goddess. India broke out of Gondwana land about 120 million years ago, in the early Cretaceous time, and moved rapidly across Tethys to begin colliding with Asia about 50 million years ago. But we have not known what ripped India from Gondwana land and sent it north. Or maybe we should say that we have not known until now. A new explanation for India's northward flight is offered in a new paper by geoscientists from the University of Texas at Dallas and published in the journal Geoscience Frontiers. Graduate student Hayu Hu and Professor Robert Stern found the answer in ancient seafloor rocks preserved in southern Tibet called ophiolites. Ophiolites are especially important for reconstructing Earth's plate tectonic history. Ophiolites consist of oceanic crust and mantle that has been thrust up on land where geologists can study them. Ophiolites consist of mantle rocks called peridotite and a variety of crustal rocks that are easily distinguished from the continental crust that they are emplaced upon. Ophiolite crust includes pillow basalt, which only forms when lava erupts on the seafloor. The Himalayan ophiolites mark the actual suture between India and Asia, where the Tethys Ocean once existed. The UTD team showed that these ophiolites formed when and where a new subduction began to form about 120 million years ago on the southern margins of Asia. The sinking of oceanic plates in subduction zones is known to be what powers plate motions. Formation of a new subduction zone on the southern margin of Asia would have pulled strongly on Gondwana land to the south, pulling India out and starting it on its northward journey. The Tethys Ocean narrowed as India moved north, consumed by the new subduction zone, until India collided with Asia to form the Himalayas we see today.
Oops, stop that. Okay, I hope you enjoyed those videos. As we said, we make videos at UTD and post them on YouTube. And if you have time and interest, one of our most popular videos is this one. It says it only has 61,000 views, but last time I checked, it had 175,000. But very wide range of topics in there. Please take a look. And also, we're looking for partners who would like to also help us make videos. Obviously, we can't easily make videos about Asia, but we would be happy to work with you to help you make yours, or perhaps to modify ours into different languages. So please contact me if you're interested. I'm pretty easy to find. Now, new research directions. I want to say something. This is an evolving field. Subduction initiation, the general concept is pretty robust. It's finding increasing applications, but what we saw with the recognition in the easy bone and art is that it was focused in the Forearc, and so it's really hard to see what else is going on because there's so much water. But in places like Iran, where we can see that there was a subduction initiation ophiolite in what's called the outer Zagros ophiolite belt, which extends into the beautiful Oman ophiolite. And we can see that this happened about, somewhere between 100 and 95 million years. But then we see other ophiolites in the back arc region and on the sides and extending in the interior. And it looks like that the extension that formed that allowed the asthenosphere to come up into this region affected a much broader part of what became the overriding plate than just the Forearc. So the full extent of upper plate extension during subduction initiation is going to have to be worked out on land. And Iran is an extremely excellent place to study this. There may be other places where this model has applications, and we encourage you to look into it. And thanks for listening. And